Hello again, everyone. Welcome to our discussion of section 2.2, where we will talk about algebra of functions. So what does that mean? Algebra of functions means adding, subtracting, multiplying, dividing functions. Just like numbers, functions can be added, subtracted, divided, and multiplied by each other. We will look at that. In particular, we will be talking about the domain of combined functions. So when we perform algebra of functions, the resulting function is called a combined function. And that combined function has to satisfy certain domain requirements. So we will look at that. Before we do that, I'd like to remind you to please read through section 2.2 or skim through it. Take half an hour to 45 minutes to skim through that section. And then attend the class or watch the video or both. And then as you review your lecture notes or the text, take notes on questions that you might have. Take notes on the important topics or excerpts or descriptions that you come across. Take note of those in your own notebook. And then, of course, complete all the solutions of the problems that you see solved in the book without looking at those solutions. And do the same thing with the problems you see me go over here in this video. Solve these problems without looking at the solutions that I give. It's really easy, right? You just pause the video, work out your own solution, and then come back to the video. And then complete all the homework assignments by the due date without procrastinating. That shows discipline. Discipline gets you results. Lack of discipline does not get you results. Okay? And of course, review, because all mathematics is cumulative in nature. So the procedures that we go through now rely on the techniques we've learned before. Okay, so having talked about that, let's begin by jumping right to an example. If we have two functions as shown, x minus 4 and x squared, and g of x equals x squared, then when we add them, this question is saying add those two functions and then give its domain. Okay, so f plus g of x is equal to the function f, right? The function f plus the function g, which is x squared. So this results in, I'd like to put my answers such that the powers are arranged in the descending order. So I'm going to put x squared first, then x, and lastly the constant. So this expression is really identical to that, but the terms are arranged differently in this order. Now the domain. The domain they're asking is very important for combined functions, because the domain of the combined function must not only satisfy the domain of the combined function, this function, but it also has to satisfy the domains of the parent functions. Okay, so that's very critical. So the domain of one of these parent functions, f of x, the domain of that function, do you see any x value that this function cannot take? Is there any restriction? No. So the domain is going to be minus infinity to infinity. With respect to g of x, do you see any x value that this function cannot take? No. The domain of this function is also negative infinity to infinity. So now the combined function, do you see any x value that the combined function cannot take? Absolutely not. All x values are acceptable, right? In particular, when I ask, is there any x value that either any of these functions can or cannot take, what I really mean is, do we have a fraction? where x is in the denominator? No, we don't. Do we have an even root, square root included? An even root or any square root, do we have that in any of these expressions? No. So the only restrictions can come from the denominator of a fraction or the radicand or the terms from inside of a radical expression. There is no other restrictions possible. So then D, or the domain of this, is also negative infinity to infinity. Now take a look at all of these. All of these agree with each other, right? So the domain of the final combined function is negative infinity to infinity. Now this one wants us to subtract those two same functions. Subtract g from f. Let's do that. So this results in x minus 4, which is f, right? And then minus g, which is x squared. Okay? Once again, let me rearrange these in the descending order of power of x. So we have minus x squared plus x minus 4. The minus that comes after a parenthesis does not distribute itself into this parenthesis. The minus, any minus, distributes itself into a parenthesis only if it comes before it. If this minus was here, I would distribute it, not if it comes after it. Okay? So we're fine there. So this is our combined function of f minus g. The domain of the combined function must agree with the domains of the parent functions. So there are no restrictions in the x in the parent functions. So is there a restriction on x in the combined function? In other words, what I'm asking you, do you see any radical expression? No. Do you see any rational function with x in the denominator? No. So there is no restriction to this. Therefore, the final domain, it's going to be, the final domain of the combined function is going to be negative infinity to infinity as well. Okay? Now we want to multiply the functions. Because I have to scroll up the paper, I'm going to write the functions again here so we can look at them as we solve this part C. So f of x is x minus 4 and g of x is equal to x squared. Okay, multiplying f by g means we're going to have to do this. X minus 4 times x squared. Okay, so x squared times x, we're going to distribute, right? X cubed minus 4 times x squared. And everything is in the descending order of power. So this is, in fact, our combined function. So we already know that the parent functions have domain negative infinity to infinity. Now, do you see any restrictions on x in this combined function? In other words, I'm asking you if you see any rational functions with x in the denominator that cannot be 0? No. Do you see any even root of that cannot have inside of the radical be negative? No. It's just x cubed minus 4x squared. So therefore, there is no restriction on x in the combined function. So therefore, the domain of the combined function is also negative infinity to infinity. Now things become interesting because next in part D, we're going to divide these two functions, f and g. F divided by g, right? So let's do that. This results in x minus 4 divided by x squared, okay? And this is our combined function. Now, we know the parent functions f of x and g of x had their domains as negative infinity to infinity. But is there a restriction on the domain or on x for this combined function? Absolutely there is, right? The x in the denominator cannot be equal to 0. So x cannot be equal to 0. The numerator is okay. X in the numerator can be 0, but not in the denominator. So as a whole, x cannot be 0. So then what is the domain of the combined function if we take out the 0? Well, let's draw a graph quickly and show this. So we're saying that x cannot be 0. That means we should have a hollow circle here. Right? Domain excludes that. That's what a hollow circle means. So what is then part of the domain? This piece and this piece, right? So according to the final combined function, the domain should be negative infinity to 0, parentheses or bracket. Parenthesis, right? Because 0 is not included. So parenthesis, union, this piece, right? Parenthesis 0, comma, infinity. So now take the intersection, compare this with the domains of the parent functions, which were both of which had their domain at negative infinity to infinity. So which domain is more restrictive? This one, right? This is saying everything except 0, but the parent functions were saying everything, right? So the more restrictive domain is the final domain of the combined function. So the final domain of this combined function is that one. So no longer negative infinity to infinity, but negative infinity to 0, union 0 to infinity. Okay, I hope this is making sense. So once again, the domain of the combined function must satisfy the domain of the combined function and the domain of the other two parent functions. It must satisfy all functions, is what we're saying, the parent and the combined function. Okay, so things are now getting more interesting because now the parent functions are both of them are square roots. So we know right off the bat the inside of this and the inside of this cannot be negative. So let's find the domain for each one. For this one, and let me bring this down a little bit. So for this one, the 9 minus x squared can be equal to or greater than 0, but cannot be negative, right? So that's our condition. 9 minus x squared must be either 0 or greater than 0. Okay? So let's solve for this x value. What do we get? We get 9 greater than or equal to x squared. So I just moved the minus x squared to the other side. Right? Now we have, let me rearrange this so the variable is on the left side. So we have x squared less than or equal to 9. This is the same thing. I have rewritten it so that the variable term is on the left side. Okay? This is the same thing. X squared less than or equal to 9. X squared less than or equal to 9. Now take the square root of both sides. Okay? Take the square root of x squared and the other side. Square root of 9. Therefore, we're going to have x squared x being between negative 3 and positive 3. So x can be between and equal to -3 and less than or equal to 3. Okay, by taking the square. So this plus or minus comes to us from the square root property. Whenever you take the square root of both sides, such that square root of both sides, the other side of where the constants are, where the constant is, gets to be plus or minus. Okay, which we had that. Then you can, how do we get x being between those? Well, you can test this. You can test this with a little diagram. Test it. If you have any doubts about that, you can start with plotting -3 and 3, right? And then test the number in this region, test the number in this region, test the number in this region, in this inequality. So if you pick a number here, -4, it should not work out, right? Because that's what we figured out. We figured out that x should be between -3 and 3. So if you substitute -4 for x, you get +16. +16 is not less than or equal to 9. Okay, so this region is not a part of the solution. Now plug in 0, something between -3 and 3. 0 squared is 0, which is less than or equal to 9. So yes, this region is okay. And then pick a number after 3, +4. Again, you end up with no. So this is a quadratic inequality. Quadratic inequalities, once you have the boundary solutions, like this case, -3 and 3, you can then use the boundary solutions, -3 and 3, in order to test each region around those two numbers. So -3 and 3 are boundary solutions. Then both numbers divide the real number into 3 regions. So test the number in each region in this inequality. See if it's valid. If it's not valid, it's out, like this one. No, that region is not valid, that region is not valid, but between -3 and 3 is valid. And also, -3 and 3 also are included, right? -3 and 3 are also included. So the domain for this function, it's going to be bracket -3, 3, and that's the domain for this function. How about this function? Well, let's see. That function, the inside of that, because it's a square root, we cannot have a negative number. So 1 plus x must be greater than or equal to 0. So solve this for x, we get x greater than or equal to -1. Therefore, the domain of this function is bracket, right, equal to -1, comma, infinity, parenthesis. Okay, so that's the domain of this parent function, that's the domain of that parent function. So now let's find each combined function and their domain. So if we add f and g, what do we get? We get square root of 9 minus x squared plus square root of 1 plus x, right? Okay, so in here, there is nothing here that is different that would make this function different than either one of the parent functions. That means the domain of this function, and we don't need that anymore. We can put that as a domain here. The domain of these parent functions are directly connected to the domain of this, which means wherever they intersect, wherever these two domains intersect is the domain of the combined function. So, I mean, you can see it right away here, what works and what doesn't work. Anything from -3 to anything less than -1 doesn't work, right? because this domain says -1 to infinity. But anything beyond 3, greater than 3 in this interval, is not going to agree with this interval. Compare these two intervals and see where they agree or not agree. As a matter of fact, let's draw a graph. So let's draw a graph to see where they agree, these two domains, and where they disagree. -infinity to infinity, and a 0 here. So that domain says -3 -3 to 3 is the solution. Right? Let me do this with a dashed line so it doesn't get mixed. So that domain says from here to here is acceptable value, including -3 and 3. I'm just putting dashed not to exclude -3 and 3, but because this is not the final domain. We're trying to figure out the final domain for the combined function. So one of the parent functions has this domain, which I've lightly shown with a dashed line here. The domain of the other parent function is bracket -1 to infinity. So that will be all of that, right? That way. So part of these two domains intersects. They intersect, right? The parts of these domains, not all of them. So this part doesn't overlap or doesn't agree with each other. And this part doesn't agree with each other, right? From here to here. So which part agrees with each other? Right there. From here to here, both domains agree. Okay? So that is going to be our domain. So the domain of this function, in fact, the x values for this combined function must vary from -1 to 3, +3, right there. So this combined function can only exist right there, where you see the thick line. Therefore, the domain is bracket -1, comma, +3, bracket. I hope this is clear. That's the only spot where the domains of the parent functions overlap, which means they agree with each other. Okay, so that's what the domain, that's going to be the domain of the final combined function. Okay, so for the subtraction, we can expect to end up with the same domain. Okay, so the only thing that is going to be different is this minus. Instead of plus, we're going to have minus. But the domain is going to be, again, -1, 3. So let's do that. Let's write this out. So this is equal to square root of 9 minus x squared, minus this time, right, because of this minus, square root of 1 plus x. So the domain of this, given the same analysis that we did for part A, is equal to bracket -1, 3, bracket. Okay, like that. Okay, so next part, part C, is when we divide the two functions, because the functions are off the screen. Let me write them down here so we can look at them as we work through this section. If you haven't paused the video already and have your own solution, please do it now. Even for part C and D, which is on the next page, it is beneficial if you don't look at this solution until you have your solution written down. Okay, so given these two functions, we already know that the domain of this function, we already figured this out for part A, it's going to be d domain is -3, 2, 3. The domain of this parent function is bracket -1 to infinity. Okay? So now let's find the combined function, which in this case is the two functions divided by each other. So f, which is that, 9 minus x squared, divided by g, which is that function. So things just got, so this is our combined function first of all. But things got really interesting because now we have a fraction. And in the fraction, we have a square root of 1 plus x. What is that going to do? Well, no longer C, when we started talking about domain C, we said that 1 plus x can be equal to or greater than 0 here. Remember that? That same function is now in the denominator, so it cannot be 0 anymore. It can only be greater than 0, not equal to it. So we need to account for that because now we have that function in the denominator. Therefore, we write down that 1 plus x must be greater than 0, not equal to 0, right? So then solve this. We have x greater than -1. So the domain of the, in this case, the domain of this function, just the denominator expression, it's going to be parenthesis, not bracket, -1 comma infinity, right? So now look at this. Take the intersection of this domain with these other two domains, right? Where do all three domains agree? The domain of the parents and the domain of the combined function. So this, we didn't need to do anything in the numerator, right? Because we already have that. We know the domain of the numerator. We already have that. That's why. But because this function ended up in the denominator, we had to guarantee that this inside is never 0. So we calculated that, and we have to exclude -1. So compare this with the domain of the previous two functions, the combined functions. So now where all three agree is that if we change this bracket to a parenthesis, then all of these domains agree. Okay? All right, so the domain then, the domain of the combined function, let me move this up. It's going to be parenthesis -1 comma 3. And that would be bracket on this side. So just because this function ended up in the denominator, we no longer can have x equal -1. Because it would make this 0, which is acceptable if you have the function by itself. If you just have g of x equals square root of 1 plus x, that can be 0. But hey, we can't have that if that function now appears in the denominator of this, right? So all I did was put this parenthesis to exclude -1 as a value of x. And now we have the proper domain. I hope you're seeing that how once you form a combined function, the domain of the combined function must also satisfy the domains of the parent functions. Okay. So here, once again, we're dealing with the same functions. Let me write those two functions here. F of x is square root of 9 minus x squared. And g of x is equal to square root of 1 plus x. Okay. Okay, so now we're multiplying. We have f of x, which is that. 9 minus x squared times square root of 1 plus x, right? So they're both square roots. The index for both roots is the same. If that's the case, we know from properties of radical expressions that we can multiply the insides. So let's do that. We can write square root of 9 minus x squared times 1 plus x. Okay. So now the domain, we can factor this, right? So recall that we made use of this special product formula in the previous video as well. If we have x squared minus y squared, if you have a perfect squared minus another perfect square, then we can write these in terms of factors. X plus 1 times x minus y. Recall that special product formula? So let's make use of it here. We can write this in terms of its factors, right? Because 9 minus x squared, 9 is 3 squared, right? Let me write that down. So we have 3 squared, instead of 9, 3 squared minus x squared times 1 plus x. So that is just like that. Therefore, we can factorize this just like that. We can say 3 plus x times 3 minus x. Okay, so let's do that. 3 plus x times 3 minus x times, of course, 1 plus x. Okay, so that is our combined function in factored form, right? But now we need to find the domain of this. Well, this is just a square root. There is no fraction involved. So this inside, the inside of this, can only be equal to 0 or something positive. So let's write that down. To find the domain, three plus x times 3 minus x times 1 plus x must be greater than or equal to 0. That's the condition. Well, let's see what makes all these three equal to, what makes this left side equal to 0. So if each of these factors is equal to 0, by the zero product property, they're all going to be 0, right? That means if this is 0, then it will make the whole expression 0 because it's being multiplied by everything else. If the middle expression is 0, it will make the whole thing 0 because they're all being multiplied. If this last expression is equal to 0, it will make the whole expression 0 because they're being multiplied. So we need to find out what makes this expression 0, what makes this expression 0, what makes this expression 0. Let's do that. So if 3, so we're finding the domain of this function. That's what we're doing. So 3 plus x equals to 0, then x equals negative 3. If 3 minus x equals 0, I'm looking at each expression in turn, then x equals 3. If 1 plus x is equal to 0, then x equals negative 1. Okay, so what does this do? What it does, it now splits the real number line into several segments. So this, we have 0 in the middle, right? X equals negative 3 would be somewhere here, negative 3. X equals, and we can have x equal to negative 3, right? So I'm going to put a solid line over it. X equals 3. There's that. I'm going to put a solid line over it. And x equals negative 1. I'm going to put another solid line over that. Look at that. These are called boundary solutions. So these are, these are boundary solutions. So the boundary solutions are very helpful, because how are we going to find the answer to this inequality if we have infinitely many numbers to check? How do we know which numbers to check? Because there are infinitely many numbers that we can substitute for x to find out whether or not the left side is in fact greater than or equal to 0. There's too many numbers to check, right? Infinitely many x values. So in order to reduce our work, in order to eliminate having to check infinitely many numbers, we make use of the boundary solutions. What are the boundary solutions? The boundary solutions are what make this numbers that make this expression equal to 0. That's it. We found those values. Those are that. Now all we have to do is check a number in this region, check a number in this region, check a number in this region, and check a number in this region. Then we're going to get a domain value for the combined function. We're going to have to compare that with the domains of the original functions, right? The domains of the original function, remember we calculated those, right? We calculated the domain of each on the previous page. For this function, the domain was bracket -3, 3. So the domain of this was -3, 3. The domain of this was bracket -1, infinity, right? That right there. -1, infinity. So what we're doing now is we're going to find the domain of the combined function and then compare it with the domains of the parent functions to see where they overlap. And that'll be the final domain of the combined function. Okay, so let's pick a number here in this region. We can say testing x equals -4 in this region, right? Any number in this region, in this inequality. So testing that, we have, plug it in. What do we have? We have 3 minus 4 times 3 minus -4 times 1 plus -4. We're asking if the left side is greater than or equal to 0. Okay, so what do we have? We have 3 minus 4 is -1. 3 minus -4, that's +4, plus 3, that's +7, times 1 minus 4 is -3. So minus is positive. We end up with +21 greater than or equal to 0. Is this a valid statement after we picked a test point in this region? Yes, it is. So it checks out. So this region is part of the domain. Part of the domain of the combined function. Not the parent functions, the combined function. Then let's test the number in this region between -3 and -1. I'm going to pick an easy number, x equals -2. It's right there, right? In between. So let's plug this -2 inside this inequality. What do we get? We get 3 plus -2 times 3 minus -2 times 1 plus -2. Right? We're asking that when we test -2 here, is the left side greater than or equal to 0? That's what we're asking. Okay? All right, so let's find out. 3 minus 2 is 1. 3 minus -2, that's 3 plus 2, that's +5. 1 plus -2 is -1. we're asking if the left side greater than or equal to 0. So we end up with -5 greater than or equal to 0. Is this a true statement? Absolutely not. Right? No. So that region where we picked our test point is not in the domain of the combined function, which is that. This region is not in the domain of the combined function. So let's test this region then. Okay? Testing x, the easiest number would be 0, right? And we're going to plug into that inequality. So we have 3 plus 0 times 3 minus 0 times 1 plus 0, and we're asking if the left side is greater than or equal to 0. We're asking this. We're not saying that it is. We're asking that. How do we ask? Because we're picking test points. We don't know. We're just testing. So we have, that's 3 times 1, right? That's positive 9, greater than or equal to 0. Is that a true statement? Yes, this checks out. So this region also is part of the solution of the combined function, not the parent functions. Let's pick a number in this region after 3. I'm going to pick an easy number, testing x equals 4, and plugging into this inequality. So we have 3 plus 4 times 3 minus 4 times 1 plus 4. We're asking if the left side is greater than or equal to 0. Let's find out. 3 plus 4 is 7. 3 minus 4 is minus 1. 1 plus 4 is 5. Multiply all these, what do we get? We get -35 greater than or equal to 0. Is that a true statement? Absolutely not. So that region is not in the domain of the combined function. So where is in the domain of the combined function? From -infinity to -3, and then from -1 to 3. Well, let's compare this with the domains of the parent functions. Let's do that. And I'm going to use a graph to do it. Here is our graph. -infinity to infinity, 0 in the middle. And we have -1, -2, -3. Like that, right? So let's, using little dots, show this domain, -3 to 3, because that's one of the parent functions. So that would be this from here all the way to this region, right? That's the domain of one of the parent functions, that box. Now let's graph this one, this domain, -1 to infinity. Okay? That's the domain of the other parent function. So -1 to infinity would be from here all the way to infinity, right? So now let's draw the domain for the combined function, which we just figured out. It's between -infinity to -3 and -1 to 3, right? Let's plot that from -infinity to 3. -infinity to -3. Sorry about that. So that would be this region. that way. That's that side. Negative infinity to negative 3. Certainly there is no overlap here, right? Except at negative 3, but that's just one number. But the rest of it, the rest of this piece is not overlapping with any of the domains of the parent functions. So we know out of this we can only accept negative 3 so far. So let's see the other piece, which was negative 1 to 3. Negative 1 to 3 is right here. This piece. That piece. So out of the two pieces, out of these two pieces that figured out would be okay in the combined function, only this area has an overlap. The negative 3 has an overlap between this and that function, but not with this function. So the only place that all three functions, the combined function and both parent functions overlap, is right here. In fact, right here, all of this. This is where all three functions overlap, which is from negative 1 to 3, right? So that's the domain of the final combined function. So that would be domain is bracket negative 1 comma 3 bracket. There. Okay. I hope this is making sense. The challenge is not to find the combined function, right? You've noticed how easily we can find the combined function. We can either divide or multiply and subtract or add, and we can easily simplify. The challenge is to find the domain. Why? Because the domain of the combined function must satisfy the combined function, of course, itself, and also both of the parent domains of the parent functions. That's the challenge. Okay? All right. I hope this is why I asked you guys to read this section before you watch the video or before you attend class, because, you know, just like you, I've been a student myself. I know that if you do that, things will really start to make sense very quickly. Okay, that's why. So if we have these two functions, once again, we want to find the combined function and its domain. So here we have to be careful. Obviously, we have fractions, and obviously the denominators cannot be 0, right? So let's write down the domain of both of the parent functions. Oh, by the way, both of them have x plus 1 as the denominator, right? So the domain of both functions is the same thing. So the domain of that means that x plus 1 cannot be equal to 0. That means x cannot be equal to, solve for this, not equal to negative 1. And the same thing. The same thing is true from the g of x function. So the domain of both parent functions, both of these guys, have their domain as negative infinity to negative 1 union negative 1 to infinity. If you have any doubts or if you have any questions as to where this is coming from, just look at this. The domain is everything except negative 1, which would make the denominator 0. So if we draw a little graph here and go from negative infinity to infinity with 0 in the middle, we're excluding negative 1, right? That would be somewhere here. Let's put a hollow circle right there, negative 1. So we're excluding this from the domain. So what is left? What's left is this piece, that piece, and this piece, right? So that, the domain that you see here for both of the parent functions is that. Negative infinity to negative 1 is that. And of course, the parenthesis means -1 is not included in the domain, which we just determined why it should not be included, right? It'll make the denominator 0. And the other piece is right after -1 all the way to positive infinity, which is that. Okay? All right. So now let's add those two functions. What do we get? We get 2 over x plus 1 plus x over x plus 1. Right? So these are common denominators. We can simplify things. X plus 1 and add the numerators because their denominator is already equal. Right? So we have 2 plus x, or if you like, x plus 2. It makes no difference. But this is our combined function, or if you prefer, x plus 2 over x plus 1. Right? Either that or this. Now the domain. So the domain of this, look at the denominator. The numerator has no problem, right? There is no square root up there. There's no fractions with x in the denominator up here. So this is fine. But what about the denominator? The denominator, once again, cannot have -1 as part of it, as x value, right? So the domain of the combined function is the same as the domain of the parent functions in this case. So we can write that as domain is equal to -infinity, comma, -1 parenthesis, union, parenthesis, -1, comma, infinity, close parenthesis. So that is the domain of the combined function. So next one, and again, if you haven't done this already, please pause the video and answer all the questions on this page on your own and then come back to it. Okay? So I'm counting on you that you took that statement to heart and you did that, and now you're back. And I appreciate that. So now I'm going to show my solution. So this one is equal to function f, which is 2 over x plus 1, right? 2 over x plus 1 minus this time g. G is x over x plus 1, right? Once again, the denominators are common, so we can easily subtract the numerators. So x plus 1 and then 2 minus x. There's the combined function. And once again, the denominator is the same as the parent functions, so we cannot have -1 again. So easily we can write the domain as -infinity to -1 union -1 to infinity. Then part C is multiplication, right? I hope these are agreeing with the solutions you have. So this will become equal to f was 2 over x plus 1. G was x over x plus 1. So what is the result? The result is 2x over x plus 1 squared. That is the final combined function. Now, this is, again, -1 plus 1 is 0. 0 squared is 0. So once again, just like before, we cannot have -1 as part of the x in this function, combined function. So the domain would be -infinity, comma, -1, parenthesis, union, parenthesis, -1, comma, positive infinity. Like that. Okay. Then dividing the functions. So f was, here we're going to get a complex fraction. So f was 2 divided by x plus 1 divided by g, which was x divided by x plus 1. Okay. So I think I mentioned before the easiest way to simplify a complex fraction. There's a very easy way to do that. Look at the numbers or entities or expressions that are farthest away from each other, 2 and x plus 1. Multiply them and put them in the numerator. Look at the terms that are nearest each other, x plus 1 and x. Multiply them and put them in the denominator. So 2 times x plus 1 in the numerator, x plus 1 times x in the denominator. Okay? Now, can we simplify anything? Yes, we can. So what do we get? We get 2 over x. And that's the combined function. That is the final result. This is very interesting because we know the parent functions could not have -1 as part of their x, right? We know that about the parent functions. But the combined function this time cannot have what x value as part of x? 0, right? So in addition to -1, which the parent functions could not have as part of their domain, in the domain of the combined function, we cannot have 0, x equals 0. So this domain should satisfy the combined function as well as the parent functions. So that means x so noting the domains of the parent functions, as well as the combined function, which is that one, then x cannot be equal to 0 and x cannot be equal to -1. There are two values that x cannot take. It cannot take 0 because of the combined function. It cannot take -1 because of the parent functions. So what do we get then? Let's draw a little graph here. So that's 0, and -1 is here. So we're saying that -1 is not acceptable, 0 is not acceptable, right? So what is acceptable? What is acceptable is this piece, and that piece. So let's write it up. The domain of the final domain of the combined function is -infinity to -1. Parenthesis or bracket? What do you think? Should I put a parenthesis here or bracket? Parenthesis, right? -1 is not included. Look at the hollow circle. Union in between the two, parenthesis, -1 comma 0 parenthesis, and then after that, right? Union 0 comma infinity. So this is the domain of the combined function after we divide the functions, right? So this was a really neat, this part D was really neat because we got to simplify a complex fraction and we got to have a new domain because up to this point the domain didn't change for the parent function as well as the parent functions as well as the combined function. It was the same domain, but now we have a new domain, right? Now we have two values that the x cannot take after we divided functions. Okay. So here, in these functions 4 and 5, notice that they're just saying find the domain of f of x, find the domain of f of x. These are much less laborious than the ones that you saw with the combined functions. With the combined functions, there are several domains you have to intersect, and you have to see where all these different domains overlap. But here, there's no mention of the parent functions, right? We're just finding the domain of a single function. There's no parent function involved here. So for that reason, we don't have to compare the domain of this with the domains of any parent functions. We can just go ahead and find the domain of this rational function. Let's do it. So the numerator, this piece, we have a square root, right? Again, I'm hoping that you've already solved this on your scratch paper, and now you're here waiting for my solution, which is great. So x plus 7 cannot be negative. It can be 0, right, in the numerator. It can be 0. It can be anything positive, but it cannot be anything negative. So we can set that up to x plus 7 greater than or equal to 0. Then solve for x here. X is greater than or equal to negative 7. Therefore, the domain for the numerator, it's going to be bracket negative 7 comma infinity parentheses. So bracket negative 7, because negative 7 is included in the domain, right? Look at this equality. How about this, x minus 6, where x minus 6 is obviously the denominator, right? And the denominator cannot be 0. So let's solve for x by making sure that this is not equal to 0. So x minus 6 equals 0, then x equals 6. So that x equals 6, we found an x value that, a value that x cannot take, right? X cannot take that value because it will make this denominator 0. So what is the domain of the new denominator? It is negative infinity to 6, parenthesis, union, parenthesis, 6, comma, infinity. Okay? That one number splits the graph, or splits the real number line into two pieces. So now, the final domain of this entire function, what we found is the domain of the numerator and the domain of the denominator. Now we got to see where both of these domains agree. Okay? So, let's draw a graph. Why not do that? We don't have to, but it's helpful if we do. So here we have negative infinity to infinity with 0 in the middle. This one says the domain is negative 7. It says the domain is this. It says the domain is that. The denominator says, no, that's not the domain. The domain is these two pieces together. So that's positive 6. So 1, 2, 3, 4, 5, 6. It says except 6, the domain is this way and this way. Right? This one is coming from the denominator. This one is coming from the numerator. So they can't both be right. We have to look at the place where they overlap. Where do they overlap? Well, they overlap from negative 7. Notice it. From negative, they don't overlap here because this is going to go this way and that's going that way. So they're not going to overlap here. So they overlap from negative 7 this way, and this is coming this way. So they're going to overlap here from negative 7 all the way to 6. So the domain is bracket negative 7, comma, 6, parenthesis or bracket. Parenthesis or bracket. It should be parenthesis, right? Because even though this is going to accept 6, this domain has no problem with number 6, but this one does. This one excludes it. So the overlapping piece is that, okay, we take from negative 7 all the way to 6, and then union then this is going to continue to positive infinity, right? So is this one. So then parentheses 6 again, comma, infinity, parenthesis. Okay, so that's the overlapping piece. And that's why graphs are so helpful. They are a visual aid, as they're called. Okay, so if we were to show the overlapping piece with a thick marker, I guess let me do it this way. So that's part of the domain. That's this piece, right? -7 to 6. And then the hollow circle excludes 6. And then the rest of this is 6 to infinity, with the hollow circle in the middle. Okay. Next problem. I hope this matches what you have in your notebook or on the scratch paper. So this one, again, please go ahead, if you haven't done this already, solve this, and then come back to the video. Okay, so I'm assuming you've done that. The domain of the first piece is that x must be greater than or equal to 0, right, from that piece. So from this, we get bracket 0, comma, infinity. That's the domain of this piece, square root of x. How about that one? Well, that one, 8 minus x must be greater than or equal to 0. That means x must be greater than or equal to, or 8 must be greater than or equal to x, right, from that. Or that, let's switch this around so the variable is on the left side. X is less than or equal to 8, right? So this is saying that the domain is -infinity, comma, 8, bracket. Okay, so where do these two overlap? This piece says that's the domain, this one says no, it's that. So let's see where they overlap. Okay, so we have 0, -3, and 8. So let me plot 8. We have 1, 2, 3, 4, 5, 6, 7, 8. So that domain says the x can be anything from here, or from here this way. That one says from -infinity to 8, which is from here all the way to here. So this one says no, this is the domain, that way. Okay, and this is 8. So where do they overlap? Right? It's easy to see where they overlap. You're looking at the graph. They overlap right between 0 and 8. Right? So let's write that down. The domain of this function is from bracket 0, comma, 8, bracket. That's the overlapping piece, right? Right there. Right here. Including 0 and 8. Like that. Okay, overlapping piece. So again, the combined functions, you have to find the overlapping piece that satisfies the domain of the combined function and both of the parent functions. But with single functions where there's no parent, we just look for the intersection of the domains for that one function only. We don't worry about the parent functions. Okay, so the difference quotient. This is something that is, again, very, very important, or becomes very important in beginning in Calculus 1 and Calculus 2, and then Calculus 3 and beyond. So this is basically the introduction to that concept, which is the difference quotient. Okay? The difference quotient basically calculates the slope of a function that has various slopes at different points along its curve. Everything for which you've calculated the slope so far in this course and previously was a constant slope. That means the slope does not change over the entire course of the function. But vast majority of functions are not like that. The function will vary throughout its course. Therefore, the slope of the curve of the function varies throughout its course. So this difference quotient is a numerical. It's a numerical way of calculating or estimating, estimating the slope of graphs at various points. So at this point, we're not interested in this in the fact that the value that it represents the slope of a function at some point. We're not interested in that interpretation of it. All we're interested in this course is that we can calculate it. Number-wise, we can calculate the difference quotient. That's all we're interested in. Whether it represents slope or something else in calculus, we're not interested in that. Okay? So this, I put this, so this is the difference quotient. That is the difference quotient, what you see there. And you can read this, I thought, to include excerpts from the textbook to just a few words. Like I say, at this point, it's not important that what this difference quotient represents. It's just that you should be able to calculate it number-wise. But if you're interested, here is an excerpt you can read about it. Okay, so how do we calculate the difference quotient? Well, one thing you should remember, and I don't know why people forget this or assume something else, but this x here, which we call the argument of the function, can be either a number, which you know very well how to calculate. If I give you this function, if I ask you, what is the value of this function at -5? Every single one of you, all of you will correctly calculate what that number should be. But you should also know that this x can take other entities. It can take 2, 3 numbers. Let me bring my scratch paper here. So this x, and this is the difference quotient, as you know, and with h, the denominator is never 0. So let me just focus on the function itself, because that's very important. I think that's where the problem, wherever people have issues with calculating the difference quotient, it's always conceptual, not numeric. But the symptom, the result, shows itself numerically, but the problem is conceptual. So this x can be number, right? Like I said, if I say guys, calculate this function at -5, every single one of you will correctly say, okay, 7 times -5 plus 2, so I got -35 plus 2, so I got -33. I've given examples like this. Every single person gets this correct, right? But what happens, I don't know what happens, maybe you can tell me what happens, once I say, find the value of this function at k plus 2. Everybody thinks, wow, how am I going to calculate this? This is no different than calculating that function at -5. But you should know that x can take any entity as its value. Can it take -5 as its value? Yes. Can it take k plus 2 as its value? Yes. Can it take this as its value? Yes. X is a variable. Variables can take absolutely anything as their value. And the function will then work on that value to calculate its what the value of the function will be at that x value. But if you have k plus 2, what will be the value of this function? Simply, wherever you see x, replace it with k plus 2. So 7 times k plus 2, then plus 2, another plus 2 on the outside, right? But x is now gone. Instead, we replaced it with k plus 2. Okay, I'm hoping you're following this, because I see people needlessly, absolutely needlessly having difficulty with this, with something so easy. So x can take any value. It could be a number like that, or it could be some variable plus some other number, or it could be something like this, or even a bigger expression. Okay, x can take any value. So then we have to, here we have to simplify, right? So distribute the 7. We get 7k plus 14 plus 2, and then we get 7k plus 16. And that's the final result. How about this? The same thing. The same thing you did with negative 5 in here. You do the same thing with it, but this time you have all of this. So please don't confuse yourself by thinking this, evaluating this function at this quantity is different than evaluating it at negative 5. 100% of you can calculate this function at negative 5. 100% of you should be able to calculate this function at this quantity. Simply substitute it wherever x is. So 7 times all of that. Plus 2. Is there any difference between what I did here and what I did here when we substituted negative 5 for x? Is there any difference between that? No. Here we had x, we substituted negative 5 for it. We had x again, we substituted this whole thing for it. Right there. 7 times negative 5, 7 times all of that. Plus 2, plus 2. So this is exactly the same thing. Don't think that it's something different. It's not. Okay? Typically in this class, a lot of points, not only my exams, but the coordinators of the exam of the course, which will design the final exam, their exams and my exams will have typically these types of questions on it. And when you miss it for no reason, it should be one of the easiest questions. It bothers us. It bothers me, and it bothers the coordinators, because we want you to get the full credit for these questions. Okay? So, having said that, then let's calculate the difference quotient, right? And note that in this case, instead of x being a number, we want to calculate this function at a plus h and then a, and then subtract and divide by h. That's all we're doing. The numbers are missing. There's no 5 or 2 or 3. Instead, we have the function evaluated at a plus h and the function evaluated at a, subtracted from each other, divided by h. That's all there is to it. So let's calculate. In order to calculate this difference quotient, again, the best way is please pause the video, calculate this, do your work, then come back to the video. Okay, so f of a, look at this. I need to calculate f of a and f of a plus h before I can calculate the difference quotient. So f of a is equal to, that means wherever x you see, substitute a for it. So 7 times a plus 2, or 7a plus 2. So that's f of a. Okay, let me write it here. F of a is equal to 7a plus 2. We have that. We have that figured out. Now let's figure out f of a plus h. F of a plus h is equal to, where you see x, replace it with a plus h, plus 2, right? Let's distribute 7 times a. So f of a plus h is equal to 7 times a plus 7 times h plus 2, right? That's it. Can we simplify anything here? No. That's it. We've got f of a plus h and f of a. We've got the two pieces we need to calculate the difference quotient. H is h. Don't worry about it. It's just in the denominator. We worry about it when we simplify things. But don't worry about what is its value. It doesn't matter. Okay, so now let's calculate the difference quotient. That's what I'll do here. Okay, after I've calculated f of a and f of a plus h, because that's what we need, I have these two calculated. Now I'm going to plug these results into this difference quotient. So instead of f of a plus h, instead of this, I'm going to plug in this whole thing, which is equal to it. Right? So parentheses 7a plus 7h plus 2 minus f of a. F of a is equal to all of that. So parenthesis 7a plus 2, of course, divided by h, right? Okay, so this first parenthesis, the terms are okay, but the second one, we need to distribute this negative. We said this before. If negative is in front of the parentheses, you need to distribute this to all the terms inside the parentheses. So let's do that. I'm going to begin with these three. So 7a plus 7h plus 2. Now we get to this minus. Minus 7a minus 2. Right? We distributed the negative over h. So now, is there anything we can do to simplify this? Let's see. Okay, so 7a minus 7a, they add up to 0. These two, that one and that one add up to 0. Negative 2 and positive 2 add up to 0. We end up with one term, which is 7h over h. Right? Is there anything else we can do to simplify? Yes. 7h over h, we can cancel the h terms. We end up with 7. So the difference quotient is equal to 7. Now it's in calculus that we tell you guys that, hey, remember that difference quotient that you worked with in Math 124 or Math 126, that value that you calculated, that represents a slope value. But in this point, we don't care. We just care that you are able to calculate this difference quotient correctly from this point to that point. That's all we care about. Okay? Let me ask you this. If we had 7 plus h over h. If we had this, could we cancel these and say 7? Absolutely not. I bring this up because I've seen this too often, and I don't know where it's coming from, because the books don't say that. No teacher ever talks about this subject like that. So where do you guys get the idea that this can happen? This cannot happen. Okay, if you have 7 plus h over h, you keep it. You keep the whole thing. There is nothing you can simplify. You keep this as is. 7 plus h over h is correct. You cannot simplify the h terms. Here, we can simplify because 7 is being multiplied by h divided by h. That's why we can cancel the h's. Okay? All right. So this one, if you haven't done this for number 7, please pause the video. Go ahead, calculate the difference quotient for this problem, and then look back at the video. Okay? It just takes you 6-7 minutes, no more than that. Okay? But it makes a huge difference in your learning of this subject. If you get into the habit of writing your own thinking down, writing your own solution down before you ask anybody else about their solution. Okay? All right, so I'm assuming you've done that, and now you're back. So this time, we still need f of a and f of a plus h, right? With difference quotient, is always like that. F of a and f of a plus h we need to calculate. So f of a means wherever I see x, I replace it with a. So a squared plus 9, right? That's f of a. I'm done. Now f of a plus h. The same way, the same thing. Wherever you see x, replace it with a plus h. So we have a plus h squared, right, plus 9. Now, we shouldn't leave this like this because later on we'd like to be able to subtract this from this and simplify things. So we need to expand this. So I'm going to expand this, and I'm going to use the shortcut formula a plus b squared. If you don't remember that, please dig it up and remember it. Dig it up from the book. I'm talking about this one. A plus b squared has a shortcut formula for expansion. If you don't remember this, you're going to have to FOIL it. FOILing is fine, but it'll waste your time, especially during exams, which is not what you want, and it's not something I want. I want you guys to be able to finish the exam. Okay? So if you have a plus a binomial squared, the expansion of this is a squared, or the first term is squared, plus 2 times ab, 2 times the first term times the second term, plus the second term squared. Earlier I was talking about 3 special product formulas that are very important to remember. This we talked about one then, right? That was this one. Well, let me write the other one. This has an equivalent with the minus in between. So again, it's the first term squared. This time, instead of plus, minus twice the first term times the second term, plus b squared. The one that I was talking about earlier is when we have perfect squares being subtracted from each other. X squared minus y squared is equal to x plus y times x minus y. There are several, there's I think half a dozen or 6 or 7 special product formulas. These 3 are very, very important. They keep coming handy and over again. If you remember these, you're going to do yourselves a big favor and save a lot of time during exams. So I'm going to apply that to this one, right? To expanding that one. What do I get? I get a squared plus 2 times a times h plus h squared. And of course, plus 9. Is there anything here that I can combine and simplify this expression? No. So this is f of a, and after simplifying, this whole thing is f of a plus h. F of a plus h. So now we can calculate the difference quotient. Let's do that here. Okay. All right. So f of a plus h, which is the whole thing here, a squared plus 2ah plus h squared plus 9 minus f of a. F of a is all of this, a squared plus 9. Parenthesis, right? Make sure you put the parenthesis there, because this minus is going to distribute itself to both terms, not just one. So minus parenthesis a squared plus 9 divided by h, right? H. So we need to distribute this minus into this and combine the terms we can with these terms. So I'm going to start from these 4 terms first. So a squared plus 2AH plus H squared plus 9. Now distribute the minus. Minus A squared minus 9 over H. Is there anything we can simplify? Absolutely. Plus 9 and minus 9, they add up to 0. A squared, positive A squared, negative A squared, they add up to 0. What are we left with? 2AH plus H squared over H, right? That's all we have left in the numerator. Is this the final solution? No, because we can simplify it, right? What can we do to simplify this? We can factor the numerator. We can factor H from the numerator, right? So let's do that. So H times 2A plus H divided by H. Remember, if you have any questions or problems with this step, remember that factoring is the opposite of the distributive property. So if you distribute this into this parentheses, you should get the numerator back. That's a very nice, easy, quick way of checking your factorization. So let's do that. H times 2A, 2AH, plus H times H, H squared, right? So the factorization works, because when you distribute this back, you get the original expression back. All right, can we simplify things now? Yes, this H and this H can cancel out because they're being multiplied by each other. Remember, we cannot simplify H if it's being added to that. If this was being added, we could not do this. We could not cancel it. No. Okay, we could combine this H with that H if we had plus, but we could not cancel it with the denominator. Here we can cancel because H is being multiplied by the terms in the numerator. So what is the result? The result of the difference quotient is 2A plus H. Like that. Okay. Number 8. If you haven't done this already, please solve this on your own scratch paper, then look at my video. Please. Okay? I'm assuming you've done that, and now you're back. Wonderful. And you have your solution in front of you. So let's calculate f of a and f of a plus h again. F of a means wherever you see x, replace it with a. So 8 minus 7 times a plus 2 times a squared. So let's simplify this and write it in the right order. So f of a, I'm going to put the term with the highest power first. So 2a squared minus 7a plus 8 is f of a. Right? We figured this piece. That's f of a, right there. Right here. Right? So let's figure out what f of a plus h is. So we have 8 minus 7 times a plus h. Right? Wherever I see x, I replace it with a plus h. Just like I said, replacing x with an expression like this is no different than when you calculate this expression as something at like 5 or 2. It's the same thing, but instead of one number, you have this whole thing. So plus 2 times, instead of x squared, a plus h squared. Okay? Now we need to simplify, right? We can't leave this like this. So let's do that. We're going to distribute this and we're going to expand that. So f of a plus h is equal to 8 minus 7 times a minus 7a minus 7 times h minus 7h plus Can I distribute this? No, not yet. Why not? Because of the power here. Remember the order of operations? I need to raise this expression to this power. Once I'm done with that, then I can multiply this with that. It's just the order of operation. So 2 times, like I said, you can either use the special product formulas or FOIL this if you don't want to remember that, but it's going to be to your disadvantage if you don't remember those formulas. Okay, so I'm going to expand this using the special product formulas. A squared plus 2AH plus H squared. Now we can distribute the 2. So let's do that. Before we, well, there's nothing here we can combine, right? Not yet. So let's continue. We're still working on f of a plus h. F of a plus h is equal to all of this, 8 minus 7a minus 7h. Now I'm going to be able to distribute the 2. So 2 times a squared plus 2a squared. 2 times 2ah is equal to 4ah. 2 times h squared is plus 2h squared. So now let's simplify this a little more. Are there any constants here that I can combine with 8? No. So I'm just going to write down 8. Are there any a terms that I can combine with this 7a, minus 7a? No, right? This is ah, which is not something a. This is a squared. So no, those are different terms than this, different category of term. So minus 7a. Is there anything I can combine with minus 7h? No, this ah is not that. So the same thing. Is there anything I can combine with this 2a squared? No, plus 2a squared. Is there anything I can combine with ah? No. Is there anything I can combine with 2h squared? No, 2h squared. So there was nothing we could combine. So this is our a plus h. Right? We needed this. We needed f of a because that's in the difference quotient. We needed f of a plus h. That's right there. So now we can combine, we can calculate the difference quotient, right? So let's do that. Difference quotient says, let me bring that all the way here. So this expression is coming from that. F of a plus h, that's this whole thing. 8 minus 7a minus 7h plus 2a squared plus 4ah plus 2h squared, right? All of that, that's f of a plus h. Minus, right? Minus f of a, parenthesis, f of a is right here. 2a squared minus 7a plus 8. Close parentheses, divide by h. I'm running out of space here, but let me try and put the rest of this here, starting here. Okay. All right. So what we're going to do is distribute this negative into that, but we're going to first write all of this down. I hope I can fit it here. I'll try. So 8, this 8, minus 7a, minus 7h, plus 2a squared, plus 4ah, plus 2h squared. Now distribute this negative, minus 2a squared. Minus 7a, positive 7a. Minus 8, minus 8. All of that over h. It barely fit, but I'm glad that I didn't have to stack up those terms on top of one another. I'd rather do this, but it's a little bit too small, and I apologize for that. I hope it's visible when you watch this video I hope those terms are visible. Okay, so, but I will post these lecture notes on Canvas as well. So you have the videos and you have these as well as notes. Okay, so let's see what we can do to simplify this expression. Can we combine 8 with any number here? Yes, we have that, right? 8 and minus 8 add up to 0. How about the negative 7a? Is there any other a term here? Yes, we have a positive 7a. So positive 7a and negative 7a add up to 0. How about the h? Negative 7h plus, no, there's no other h term. I mean, just like that. So let me write that down, minus 7h. How about 2a squared? Let's look. Right there, we have minus 2a squared, positive 2a squared. So these two add up to 0. How about ah? Are there any other ah terms? No. So we write down 4ah. Then how about any h squared terms? No. This is the only one. So plus 2h squared. And we already know that 7a and minus 7a and negative 8 and 8 have added up to 0. So that's that over h. Can we show that as the final answer, or is there anything else we can do? We can do more, right? We can simplify. Look at the numerator. What can you factor? You can factor h. H is in every term, so we can factor it out. Can we factor 2? No, because 2 is a common factor of 2 and 4, but not 7. So we can factor out 2, just the h. So let's do that. H times, again, the factoring is the opposite of the distributive property. So when I'm done factoring, when I distribute the h into this parentheses, I should get this expression back. What should I put here to multiply by h and get negative 7h? Negative 7. What should I put next after this plus so that when I multiply it by h, I get 4ah? Well, 4a. What should I put next here so that when I multiply it by h, I get 2h squared? Well, 2h, right? 2h times h is 2h squared. So just test this. Distribute this into that on your own scratch paper. You should get that expression. All of this over h. So now this h and this h cancel out because that's being multiplied. And the result is, I'm going to write it in red because this is so crowded that I want it to stand out, the final answer. So the final answer is minus 7 plus 4a plus 2h. There's the final answer. Okay, that's 4a. All right, so we've come to the conclusion of another section. Thank you for persisting through this video. And like I say, the key to these videos being very useful to you, the only key, you hold that key, not me, honestly. And the key is that you do not just watch me work these problems out. You write your own solutions down before you watch the solutions that I give. So you should be pausing the videos repeatedly. As soon as I get to an example, you pause the video, you work it out on your own, then you unpause the video to see what I did. And if our answers agree, fantastic. If they don't agree, maybe I made an error. Bring it to my attention. Ask a question about it. Okay? So again, thank you for persisting through this video. Have a nice day for now, and I'll see you all next time.